Okay, welcome to lecture 8. Sorry, not 8, lecture 5 of our computational microelectronics course. So, although this is already lecture 5, so due to my busy trip, actually lecture 3 and lecture 4 were just pre-recorded, and I hope that all of you have already watched that those videos. So today we will continue our discussion on Newton method to um, the MOS capacitor. So let's go to the main contents. Okay, so our goal is to develop the compact charge model. So in previous lecture 4, we have discussed about the relation between surface potential and surface electric field. So at the time it was written as this way and evaluated at x equal to 0, but this is actually corresponding to the electric field, because electric field is under the electrostatic approximation. It can be written as this form. So in our one-dimensional case, in 1D case, it can be just written as minus times first order derivative of the electrostatic potential with respect to the real space position x. So although we are write down in this way, but it is actually corresponding to minus times x directional component of electric field. So this is closely related to the charge inside the semiconductor. So to us it is really important. It means that if we have a certain semiconductor structure and if we have a certain grounding at this substrate region, and if we can control the surface potential at this boundary, then actually we can control also the number of charges collected at this point nearby the surface point. So it is quite much important, because we will use this property to control the number of electrons or holes inside our MOS field effect transistor. Okay, I assume that all of you understand the basic MOS capacitor. Okay, so in our previous lecture, we have already covered the MOS capacitor, but not in its entire structure, but only the semiconductor part. But today, we will start from the entire MOS capacitor with its oxide layer. Of course, we must do it, but in order to make it easy, so we intentionally neglected the oxide part in a previous case. When you have a MOS capacitor, actually you cannot control directly the potential at this interface point. So how can you change the potential directly? There is no way. Instead of that, when we have oxide on top of silicon substrate, and when we have gate metal, then this gate metal to connected a certain voltage source, and by controlling the magnitude of this voltage source, we can indirectly control the surface potential at that point. So point is, although our ultimate goal is to change the number of electrons collected at this point, but this is not directly accessible to us, so we always have to do something like this: change of gate voltage, which is eventually transferred to the change of surface potential. And when we change the surface potential, then eventually that will introduce change of our electron density. So we will use this change of electron density to quantify the operation of our MOS capacitor and field effect transistor. So since now we can well understand the behavior of this how can I say the silicon part, substrate part, now we wanted to make it complete by adding this oxide resin, and now we wanted to draw certain quantities as a function of gate voltage. For example, as a function of gate voltage, we wanted to calculate certain kind of charges collected in the semiconductor resin, or sometimes inversion charge. So we can do it by performing today's study. Okay. So now let me just repeat the problem specification. That is quite much similar with the previous one, but a little bit different with this oxide layer. P-type substrate, a silicon substrate, is regarded as homogeneously doped with a constant Na. Of course, in reality, Na is not a constant. Doping concentration can vary as a function of a position variable. However, we will assume, for simplicity, we will assume this constant doping density, and interface is located at x equal to 0 here. And now we have additionally introduced oxide layer whose thickness is written as a T ox. So in our coordinate system, so since interface is denoted x equal to 0, so we will say that here we have x equal to minus T ox to represent the starting point of our oxide layer. Of course, here we have metal gate, and we can directly control the voltage applied to the metal gate. Actually, in reality, here now we have a voltage source, and here we have the interface between metal and oxide. So in reality, there can be also a certain resistance, and also due to this resistance we can expect small amount of voltage drop. However, in this case we neglected this effect because in this MOS capacitor there is no current, so there is no voltage drop, and even when we have a small amount of gate current, but that current is so small when we consider normal operation, so we don't care about the voltage drop across this gate metal. So your gate voltage is directly applied to this point, and now we will consider what will happen if you change your gate voltage, then what will happen to your surface potential. So that is the thing we wanted to do. Okay, so in order to perform this kind of analysis, we need to introduce the permittivity. Oxide permittivity is written as epsilon ox. Yes, sometimes it can be treated as a relative quantity, but in this presentation I will treat this number as just permittivity. It means that, for example, it can be regarded as 3.9 times our vacuum permittivity. Okay, so please understand this is the real permittivity, not a relative one. And now every quantity of our interest is written in the form of electrostatic potential phi, or sometimes more precisely we are now representing our quantity as a phi bar, What is phi bar? That was the phi electrostatic potential referenced to the value at the deep substrate. So actually this value, the position here far away from our interface, this value is taken as epsilon of phi infinity, and referenced to this value we calculate this phi bar. Sometimes it is closely related with band bending if we represent in terms like energy variable. However, anyway, this is the electrostatic potential referenced to the deep substrate. Okay, so now we wanted to know what is the boundary condition for our electrostatic potential at this point. Which point? Yes, this point. In previous lecture 4, we just saw that okay, we know the values like phi sub f at this point, but now we cannot expect such kind of a simplification, so we have to anyhow find out certain relationships between our gate voltage and the potential at that point. That point means that minus T box point. Okay. So gate voltage has the unit of voltage. Also electrostatic potential has the unit of voltage. So if you use just to think naively, then maybe you may say, okay, so this is the one we will have. However, certainly it's not the case, because this is the terminal voltage applied to our gate terminal, or if we consider other different terminals, then this is terminal voltage, and this is the electrostatic potential. This is electrostatic potential, and they have different meanings. So we need to convert one from to the other. Okay, so how can we find out the values of electrostatic potential at gate? So that is summarized in this slide. In order to understand this slide, first of all, we have to understand this one. You must remember this or understand this relation. So we have introduced electrostatic potential. So that is written as electrostatic potential. However, point is, sometimes important quantity like electric field is just obtained not directly from this electrostatic potential, but we have if we have a relation looks like this. It means that if we introduce a global constant C to this electrostatic potential, then even in that case, that does not change our observable electric field. Even when you have a certain position independent constant to your electrostatic potential, then that doesn't make any difference. So that is the problem. Okay, then how can we set the reference of our electrostatic potential? What does it mean when we say electrostatic potential equal to 0? What is it? That is the main question of our study in this first part. So the answer is quite straightforward. So in order to represent this electrostatic potential, we conventionally introduce this notation. So please understand this is not like a universal convention, widely, universally adopted everybody. For example, if we go to certain physicists and ask them about this notation, then they will say that, oh, there is no predefined convention for electrostatic potential. But we have to understand this convention is widely adopted, at least the guys in TCAD field. So means that in a field of computational electronics, everybody in this field understand this convention. Okay, so simply means that, so let me just explain a little bit further. So this is electrostatic potential, and by multiplying minus q, so this is elementary charge, then we can convert it to the energy variable. So previously it was in a unit of volt, and now by multiplying this minus q, we convert it to EV quantities, energy quantity, and this energy just to represent this E sub I quantity. Then what is E sub I? In this case, we represent E sub I intrinsic Fermi level of the reference material. Okay, so are you with me? So for example, if we have the reference material silicon, then of course we have EC and EV, and in between, quite close to the mid-gap energy, we have a certain energy level called as intrinsic Fermi level. When the Fermi level is located at this point, then we can expect that we can find electron density of intrinsic carrier density in conduction band, and also we can expect hole density corresponding to intrinsic carrier density. So intrinsic Fermi level is the level to equate the electron density and hole density. So every time we can define this E sub I value. So simply speaking, when we say the electrostatic potential at a certain position, then by using this relation, you can always find out intrinsic Fermi level of your reference material. Please understand, always I'm saying this intrinsic Fermi level, I always add a certain limitation like of the reference material. So please, let's come back to our system, MOS system. Here we have metal oxide semiconductor system, and we have at least two different materials. What is it? One is silicon and one is silicon dioxide. So in this case, even though we have two different materials, but silicon is taken as the reference material. So simply speaking, even when we consider a certain point inside this oxide layer, our electrostatic potential, when it is converted into energy variable, then it should describe the EI of what? Of silicon, not silicon dioxide. So are you with me? So although this point is belonging to the oxide layer, actually there is no silicon at all. So there is only silicon dioxide. However, your electrostatic potential should point out the intrinsic Fermi level of not silicon dioxide but silicon. Then of course the natural question is, well, there is no silicon at all, then how can we find out this silicon's intrinsic formula level? So you can do it in this way. Even though we don't have a silicon, but we can always define the vacuum level, and from this vacuum level you can always find out certain distance between your vacuum level and intrinsic formula level of your silicon material. So simply speaking, even when you have just silicon dioxide, so you can convert it to the formula level, or you can find out the formula level of silicon. So that is the way to quantify the electrostatic potential. When you first hear about this story, so maybe you feel a little bit confused. Why? Because this is just a silicon dioxide. Why don't you just use the intrinsic formula level of silicon dioxide? So also if we have different materials, maybe we can just follow the material composition. Then that will be quite easy to follow. However, there was a certain historical development of this convention, and they means the researchers in this field agree that it is better to use just the reference materials intrinsic formula level as the quantity to be pointed out by our electrostatic potential. So please always be careful that the quantity to be pointed out by the electrostatic potential is the intrinsic formula level of the reference material. Then how can we get the reference material? This is another question. For example, in this case, silicon dioxide and silicon. In this case, it is obvious that we must set the silicon as the reference material. But let's consider the case we don't have any silicon at all. For example, if you consider 3,5 material, 3,5 device, then there is no silicon at all, and everything should be, for example, a gallium nitride and aluminum gallium nitride or something like that. In this case, which one should be the reference material? The basic rule of thumb is if we have multiple devices, then usually we have some tendency to take the material with smallest energy band gap as the reference material. For example, silicon dioxide has the band gap almost close to 9.0 electron volt, and silicon dioxide, of course, we have quite a relatively small band gap, so narrow band gap, like 1.12 electron volt. So it is obvious to take silicon as the material for our reference. Okay, so usually when we have multiple materials, then usually the material with narrowest band gap is used as what? Used as the channel material, and all other materials are just treated as insulating materials. So, we just reference the channel material because our main purpose is to consider transport behavior of our electronic devices. So, in my opinion, that is quite reasonable to take it as the reference material. Okay, so anyway, so I think that this is a really important message you must understand. Basically, there is no universal agreement about the reference of electrostatic potential. However, at least in this field, TCAD field, people agree that we have to introduce this convention. So just by multiplying minus Q to our electrostatic potential, we try to figure out the intrinsic Fermi level. Then the next question is, then at the interface between gate metal and oxide, what will be the E sub I of the our silicon material? So let's do it together. Okay, so now let's say that for Y gate voltage is 0. It's okay. So for gate metal, we can define work function. Work function is defined as the energy difference between the vacuum level and the Fermi level. So the reason why I assume here Vg equal to 0 volt, then it is corresponding to the Fermi level of the gate metal is now 0 electron volt. For example, instead of that, if we have the condition like gate voltage equal to 1.0 volt, then we have to say the Fermi level of the gate metal is now, instead of this 0 electron volt, it should be minus 1.0 electron volt. Okay, so are you with me? Simply speaking, when you have a certain gate voltage, by applying once again minus Q to your voltage value, then you can estimate the Fermi level of your gate metal. So in this case, in this 0 electron volt, certainly now you have 0 electron volt, and this is the Fermi level at your metal gate. And in this metal gate, you can also well define the work function. Work function means the energy difference between this Fermi level and vacuum level. So where can you find this vacuum level? Okay, by adding the work function, now you can point out the vacuum energy level. And this is a gate metal, and here we have silicon dioxide, and now we have the interface between these two materials. However, even in that case, vacuum level is free from the restriction of our material. I mean that vacuum level means the level experienced by free electron. Already this electron is overcoming all kinds of restriction done by our material composition, so it does not see any kind of discontinuity when it crosses this gate metal and silicon dioxide interface. So from this consideration, it is obvious that here, even in this point quite close to the boundary, our vacuum level will be continuous that of our gate metal. So simply speaking, I would like to say that vacuum level, even in this silicon dioxide boundary, equal to the, sorry about that, this one, so metal work function. Okay, so now here we have silicon dioxide, but the quantity we have to find out is no longer silicon dioxide's intrinsic Fermi level. Instead of that, what we have to evaluate is the intrinsic Fermi level of our silicon material. Then how can you find out the silicon material's intrinsic Fermi level? There are two steps. the first step is, okay, try to find out the conduction band of our silicon. Okay, and usually this energy difference is well defined. What is the energetic difference between conduction band minimum and vacuum level for silicon? This number is known, and this number is usually called as electron affinity. So since the electron affinity of a silicon material is already known to us, so usually that is written as chi. So simply speaking, in our current setting, so EC of a silicon can be well represented as metal work function minus chi. Then we can point out the conduction band level of our silicon material. Of course, once again, there is no silicon at all in this point in reality, but we have to find out our artificial or the silicon material in our mind, and we have to find out this EC. After that, if we know once again the difference between EI and EC of a silicon material, then by taking this difference, if we know this difference, then we can eventually point out the intrinsic formula level of our silicon material, in this case, or reference material. Then natural question is, work function. Do we know the work function? Yes. When you have a certain gate metal, then usually you know this number. And how about the electron affinity? Yes, if you have a silicon material, you know the value of a silicon electron affinity. It's about 4.05 electron volt. And finally, the question is, what is the difference between EC level, conduction band minimum level, and EI? So you know that this is quite close to the half of your band gap energy, and this is just a rough estimation. And when you know exactly NC and NV effective dose of the conduction band and effective dose of your balance band, you can accurately calculate this EC minus EI value. So from all of these calculations, now you can exactly calculate EI level, intrinsic formula level of your reference material silicon. Then now when you know this intrinsic formula level, by applying this convention, what you have to do is just taking minus Q. So you will have this expression for your electrostatic potential. Okay, so looks quite complicated, but don't be bothered by this seemingly complicated expression. The rule is quite simple. What was it? We just made the use of continuity in its vacuum level. Although all kinds of quantities can show discontinuity at this boundary, because you know here we have a gate material metal and silicon dioxide, everything can be different. However, if we consider the vacuum level is not belonging to a specific material, so it should be continuous. So by using the continuity of the vacuum level, we have arrived at this expression. Okay, and when up to now we have thought about the case where gate voltage equal to 0. However, if we have a non-zero voltage, then obviously we have the additional factor coming from applied gate voltage. So are you all with me? So you can do it. So let's just consider a rough estimation about these numbers. This is really rough estimation. The reason why I call it as a rough is sometimes our metal work function can vary quite a lot. So for example, if you have a 4.1 electron volt, so 4.1 EV, this is usually the values for our N MOSFET. If you are working with the P MOSFET, usually you wanted to use much higher value, like close to 5 electron volt. But for example, so this one has a quite much distributed depending on your device, but for a while just to say that this is the typical number. And how about chi? So this is just a given number, so this number. And how about this EC minus EI value? Of course you must do the exact calculation, but roughly it is around 0.56 electron volt, because you know band gap is 1.12 electron volt. So please try to calculate it. So when you just calculate that value, you will have 0.0 EV minus 0.56 EV, so minus 0.51 EV will be the energy level of your intrinsic Fermi level of silicon when you have this problem. Okay, so are you with me? For example, instead of this number, let's consider another extreme number. When your metal work function is not 4.1 but 5.0, which is quite good for your P MOSFET, then what will happen? You have additional 0.9 volt, 9 electron volt for your calculation. So instead of this number, you will just add 0.9, then you will have 0.39 EV as the value for your electrostatic so the value for your intrinsic Fermi level. Of course this number will be converted into, when you have minus 0.51 EV, then that will convert it into just 0.51 volt positive. And when you have 0.39 EV, then it will be converted into minus 0.39 volt. So please note that there is always a sign conversion between energy and voltage, but please don't be fooled by this conversion procedure. Okay, so the answer is, what we have done up to now is we wanted to consider this MOS capacitor a little bit more generalized system than just a silicon substrate. And in this case, what we have to do is to introduce the boundary condition at this point, and we wanted to know the electrostatic potential at this metal oxide boundary, and the answer is it's not that easy. So the answer is, wow, we have to calculate this quantity. Of course, all of these quantities are known to us, so we can evaluate it. But anyhow, in your problem, those numbers should be given to you. Okay, so once you know those numbers, then you can just fix that value. So now let's consider this one. Sometimes since this is quite long and lengthy, so we wanted to more intuitive expression about this value, flat band voltage. So up to now we have discussed about the electrostatic potential at minus T aux point. However, this is just phi, the electrostatic potential. The quantity we are using currently is not this electrostatic potential, but electrostatic potential referenced to the deep substrate. So if we have this phi bar, so referenced to the deep substrate, then of course we have this reference value. Nothing has changed. So now think about this one. In this electrostatic potential reference to this deep substrate, it simply means that if this value at a surface is positive, then we are now considering this upward bending of our potential. For example, if you consider negative value of this phi bar quantity, it means that we have downward bending of our electrostatic potential. So depending on the sign of this phi bar quantity, we can say that this is upward bending or downward bending. So then naturally we can ask ourselves, how about the boundary between this upward and downward? If we say phi bar equal to 0 everywhere, it means that there is no bending at all. So starting from this deep substrate, our electrostatic potential is just constant all over our system. So if we have this condition equal to 0, then we can find out the gate voltage to realize the flat electrostatic potential profile. So what is it? Simply speaking, this condition is obtained by taking the negative of this term, and here we are having this expression. Simply speaking, when you apply the gate voltage or flat band voltage, then you will have the phi bar quantity equal to 0. It means that there is no bending at all. So this is the one we will have in our simple MOS case. So therefore, since this entire term can be represented as just minus of flat band voltage, so it is quite easy to say that our phi bar quantity at this metal oxide boundary is simply given by minus flat band plus applied gate voltage. Wow, that is quite easy to represent, but please note that in order to derive this expression, flat band voltage in order to calculate flat band voltage, we have to understand work function, electron affinity, and half of band gap. Also, we have to understand the doping concentration of our silicon substrate. All of these quantities should be known to us. Okay, now anyway, so in terms of phi bar quantity instead of the phi itself, now things becomes a little bit easier. So I'm quite happy with this one. So with Okay. Okay, sometimes this display can be a little bit stuck, so let's wait for a while. Okay, so now it is released. So in this phi bar variable, now we have this kind of well-defined values. For example, at deep substrate, of course our phi bar value is equal to 0. Why? From its definition, we reference the values at this point, so it is quite easy. And up to now, we have discussed about the phi bar value at gate side, and it is given as minus flat band voltage plus applied gate voltage. Now, our goal, our analysis is aiming to calculate this phi s value at this point. Although phi s is written as just electrostatic potential, always please note that this is nothing but electrostatic potential at interface reference to the deep substrate. So we have to understand phi sub s surface potential itself always already referenced to this deep substrate. Wow. So now we have two boundaries. We know this boundary and we know this boundary, and our goal is to calculate this value, phi s value. We will treat this phi s value as an unknown variable. We will try to solve the nonlinear equation for this phi sub s. So, well, how can you do that? Previously, in lecture 4, we just set the value of phi s at here, or in your homework problem, instead of setting the value, instead I gave you certain conditions evaluated at x equal to 0, and you were able to calculate the phi s by solving the nonlinear equation. But now your system is little bit extended and your boundary are shown here, and then it means that you must also introduce a certain condition for quantity 4 here, and it is no longer a given value. So how can we get the solution? We must introduce a new solution, additional solution, and at x equal to 0, the continuity of what? Continuity of this derivative. No, it is corresponding to the electric field, but electric field is not continuous across the material interface. Instead, the normal component of dielectric field, dielectric vector, normal component of dielectric vector should be the continuous quantity. So simply speaking, if we say without this one, and if we have state in this way, we are now saying that continuity of E field, the normal E field, but this is not the case in our MOS case. Instead of that, we have to state in this way, multiplying the permittivity to the electric field, and this is corresponding to the continuity of normal component of our D field displacement vector. Okay, so we have to have this D field continuity. Okay, so if you don't understand this one, I think that this is a really important important fact you must know already. And if you don't understand this one, then please revisit your electrostatic course. Then now, then let's think about this one. Do you know the oxide permittivity? Yes, this is a given number. And do you know also silicon permittivity? Yes, this is a given number. Then how about this first derivative of your electrostatic potential? Here you have 0 minus and 0 plus. What does it mean? This is the electric field evaluated at your silicon dioxide part, and this positive part is corresponding to the electric field evaluated at your silicon part. Fortunately, in our previous lecture, we have studied about this quantity. It can be represented as a complicated function of surface potential. Now, although that is quite lengthy, but you know it. Then, how about your electric field inside the silicon dioxide layer? That is the remaining key to fulfill this condition. Okay. So, equation to be solved when we have a positive surface potential upward potential bending, not bend, but potential. So in this case, we can express our right hand side as like this. So how can you do that? Please visit your previous lecture, lecture 4. You can immediately find this expression. But how about the field in this oxide layer? So it is quite easy to perform. So let me just do it. Now here you have values of minus flat band voltage plus Vg, and here you have surface potential. So in order to calculate this slope of a straight line, what you have to do is just to take the difference between phi s minus what? Flat band voltage and Vg. What I did is just to take the difference between this value and that value. Also, it should be divided by what? The position of this value, 0, and position of this point. Okay, so 0 minus T ox. Simply speaking, this calculation will yield just T ox in lower part and phi s plus flat band voltage minus gate voltage. So it's not that difficult to understand this simple calculation. So you will have this expression. This is corresponding to the slope of your electrostatic potential and multiplied by oxide permittivity. This will be left hand side of your equation, and right hand side, this information can be obtained from your previous lecture, lecture 4. Okay, so then now you understand the right hand side of this equation can be physically understood as the quantity of semiconductor charge. Okay, so how can you understand this expression? So although you feel that you understand this relation, so can you derive or prove this relation from what? So please start from the Poisson equation and please integrate this Poisson equation inside the entire semiconductor region. And also you have to apply this quantity. If you go into deep substrate, of course electric field vanishes. So the only remaining thing is the electric field at interface. It does not vanish. And when you rigorously integrate your Poisson equation without further approximation, you will get this relation. Please do it by yourself. Although it is quite straightforward and simple, but please do it by yourself. I mean that you have to understand the procedure, the reason why this quantity is regarded as surface, not surface, but semiconductor charge. Okay, so anyway, the right hand side can be regarded as semiconductor charge, and this one has the unit of, for example, Coulomb per square centimeter, because this quantity is already integrated over the semi-infinite silicon region. So usually our net charge density has the unit of Coulomb per cubic centimeter. However, when it is integrated along x direction, so now we will have the quantities like Coulomb per square centimeter. And now you have a very well known expression like this. From this expression, we can introduce oxide capacitance, and this oxide capacitance is once again not exactly capacitance itself. The unit of capacitance is usually called as farad. However, this quantity is no longer farad itself. This one is farad per square centimeter per areal capacitance. And by using this areal capacitance, now we can have this final form shown here, and it has its own name. So quite frequently it is called as MOS equation, the equation for our MOS capacitor. So in our previous lecture, lecture 4, we have already shown that the relation between surface electric field and surface potential. However, that is not called as a MOS equation. This equation is called as the MOS equation. The point is, the main message of this MOS equation is, when you change your gate potential, it is not fully related to the change of your surface potential. Although you wanted to change the surface potential, sometimes you cannot. When you change your electrostatic potential, your incremental gate voltage is divided into two parts. The first part is the one consumed by this semiconductor part, and another one is bending of a surface potential. Okay? So actually, if we more precisely state, when you apply additional gate voltage, then potential is further bended, and that is used to bend in silicon part. This is just showing, so bending in semiconductor region, and this is corresponding to the bending in silicon dioxide region. Okay. Simply, if I give you 100 Korean won and if you divide it into among you guys, four guys, then the sum of the entire increase of your pocket money will be the same. However, the exact ratio between your pocket money increase will be different. This is just written as this MOS equation. So by solving this MOS equation, you can get the surface potential phi sub s, and from this phi sub s you can always calculate the surface charge, the semiconductor charge, and from this semiconductor charge you can also estimate the inversion charge, which will be used for your transport purpose. Okay, so well, although it is given as a well-known MOS equation, but please note that gate voltage is just a number. Flat band voltage is also a number. The only unknown variable is surface potential. Well, here we have surface potential. So what is the solution? Surface potential is Vg minus V flat band plus Qs C ox. That's it. No way. The problem is here Q sub s, semiconductor charge itself, is a complicated function of our surface potential. So this MOS equation should be treated as a nonlinear equation of the surface potential. So we must solve this nonlinear equation. As long as the nonlinear equation is involved, our method is Newton method, and now it is straightforward to implement the Newton method. What we have to do is first identify the equation. The equation is this function should be nullified. Okay, this is treated as a function of a surface potential, and when you evaluate this function, its evaluated value should be 0. If your test value for surface potential does not satisfy this 0 condition, then you are wrong. So you must update your surface potential. And in order to find out the numerical solution, then of course you have to find out the derivative of your function with respect to surface potential, and fortunately you can do it quite easily. For example, please try to make a derivative with respect to phi sub s. This is a number, so does not contribute. This is a number, does not contribute. And how about this? Phi sub s, when derived with respect to phi sub s, it will give us just number 1. And the only complication comes from this one, because Qs is a function of phi sub s, so we must calculate dQs over d phi s. Then how can we calculate this number? Fortunately, now we have full expression for Q sub s when phi sub s is positive. So by taking the derivative with respect to phi sub s, although lengthy, but you can calculate it. It is lengthy, but yes, you can do it without any problem. So now, by performing the function evaluation and calculation of this derivative, you can apply the Newton method and you can get the solution. Let me show you an example. Let's try to calculate surface potential. For example, so what does it mean 1.0 volt? So it means that when gate voltage equal to 1.0 volt, please try to calculate phi sub s. Assume that your metal work function is 4.1 eV, and yes, electron affinity is given as 4.05 eV, and also NC, so effective dose of conduction band is also given, and intrinsic carrier density, yes. So when you calculate this number EC minus EI, as I told you before, it is about roughly 0.56 eV, so you can calculate exactly. Also, when the p-type doping concentration is 10 to the 17 per cubic centimeter, from this condition you can calculate phi infinite, the phi at deep substrate. So collecting all of these quantities, finally you can identify your flat band. In this case is about minus 0.9 if minus 0.2 volt, and when gate voltage is 1.0, yes, so phi bar should be given as minus 3 flat band plus gate voltage, so you will have this boundary condition. Well, now you understand if this is real space position and this is phi bar quantity, and now you understand in your left boundary your value is about 1.9 volt, and your right value, boundary value, is 0 value, and you wanted to calculate the value at this point x equal to 0 by solving the MOS equation. When oxide thickness is 10 nanometer, and by applying, for example, a certain Newton method, you can easily find that this is the value for your surface potential. What is it? This third column just shows the update of our surface potential. So maybe you may ask me why your very first delta phi value is so small, like just less than 1 millivolt. Is it because I did not jump into this 1.0 volt case directly? I started from a certain low gate bias voltage and slightly increase values toward the real value, the target value 1.0. That's the reason why my update value is not that high. But anyway, we can eventually get the solution. And please have a look at this final paragraph. How about the case when we apply additionally 0.1 volt? Instead of 1.0, now we have 1.1 volt. Well, now we applied additional 1 volt, now it becomes 2.0 volt. Previously, when it was 1.9, its value was 0.95 volt. And now, when you increase it to 2.0, how does it look like? Although you have increased the gate voltage 0.1 volt, but please have a look at the difference between surface potential. What is the change of your surface potential? Surface potential is increased just by 6 millivolt. You have increased 100 millivolt to your gate. However, surface potential does not change 100 millivolt. It just changes 6 millivolt. The remaining 94 millivolt is applied to what? To your oxide layer to increase the the inversion charge density. So it is only because our gate voltage is sufficiently high, so already this MOS system is in its strong inversion regime, so surface potential is more or less pinned, almost fixed, and additional gate potential, additional gate voltage always just to increase the amount of inversion charge density. Okay, so I think that although I have shown it only for strong inversion reason, but you may play with different gate voltages, then you can get further insight on the behavior of a MOS capacitor. So now I will announce our homework number 5. Okay, please consider our MOS system. The parameters are the same in our example. So 10 to the 17 per cubic centimeter, and oxide is 10 nanometer. Please note that 10 nanometer is extremely thick from the viewpoint of state of the art. Actual value nowadays is no longer 10 but less than 1 nanometer. So why do we consider this really thick oxide? It is just educational purpose. But if you are working with the state of the art device, your target value should be not exactly 1.0. Nowadays, even 1.0 is regarded as a little bit thick, and engineers are aiming to achieve 0.9, 0.8, 0.7 nanometer as an effective oxide thickness, not physical but effective oxide thickness. And anyway, using the same MOS system, please try to calculate your surface potential as a function of gate voltage. How can you do that? You can just solve your MOS equation. Once you solve the MOS equation, you can get this beautiful graphs. So as you can see here, now when your gate voltage is 1 volt and potential, surface potential is more or less fixed around this 0.95 volt, even though you increase it to 1.1 volt, but it only shows really small increase in your surface potential. So this one shows surface potential pinning, and in this part, of course, when you change your gate voltage, it directly converted into the change of your surface potential. Okay, so in in the sub-threshold region, so when you change your gate voltage, it is directly converted into the change of your surface potential, and once the device is turned on, then surface potential is more or less fixed and it does not increase any further meaningfully. Okay, so thank you for your attention up to now, and I have to announce another 2 recorded video. So due to my business trip to San Jose, next week we don't have any online on-site lecture, so I have already uploaded my 2 pre-recorded videos. However, that is not open to you, so only when you have your lecture time on time it will become public. So please leave your message when you watch those videos. And of course you have also homework number 6 and 7. I'm really afraid that the difficulty of homework number 7 is high, too high to most of you. So please be careful and please do your best to perform homework number 7. Already when you do homework number 7, you have done most of jobs required in this semester. So the due of homework number 5, number 6 and also number 7 will be October 8th, so several more than 2 weeks later. So you have sufficient time. So please concentrate and especially achieve this number 7. The main contents of homework number 7 is exactly same with this homework number 5. However, today we have done homework number 5 by solving just MOS equation. This MOS equation is regarded as an equation for surface potential. That was done in our today's lecture, and in lecture 7 you have to do the same thing, however keeping the position dependency over all of your electrostatic potential. Instead of calculating only electrostatic potential, but you have to calculate the entire profile of electrostatic potential. That should be done in your homework number 7. So I'm really afraid that maybe that will be too difficult to you. So my warning is, when you spend sufficient amount of time and effort, you can do it because all available resources are in our YouTube channel. So please do your best to do all of homework number 5, 6 and 7. Okay, thank you for your attention and let's wrap up today's lecture.